probability. I'm going to start by talking about Venn diagrams and mutually exclusive events. So let's look at the diagrams on the right-hand side. The circles in the diagrams represent events that we would need to define. A could be rolling a die and the probability that the die rolls a number less than 2. And B is the probability that the die rolls a number greater than 4. So let's think of what the possible outcomes are when we roll a die. The outcomes are a 1, a 2, a 3, a 4, a 5, and a 6. All of these possible outcomes are called our sample space. So given the fact that an event involves rolling a die, these are our possible outcomes. So each one of these is an outcome. So with event A, the possible outcome when we have a number less than 2 is 1. And for event B, the possible outcome for a number greater than 4 would be 5 and 6. Now in our Venn diagram, what we would do is we would take the numbers that are in our sample space but not included in the events, and we'd leave them in this rectangle that's outside of our circles. So 2, 3, and 4. The entire Venn diagram is the rectangle with the circles, and it shows our complete sample space. It shows the numbers 1 through 6, which are all of our possible outcomes, and we have separated the outcomes into events. Mutually exclusive events means that we have no overlap in outcomes. Now you will see some examples where just by the definition of the events, we have shared outcomes, and that means our Venn diagram will appear a little bit different, so you'll see that in one of the examples. In the example that I'm showing above, I want you to notice a couple things. So when you're finding the probability of event A or B, you take the probability of A and you add it to the probability of B. So a really important thing to remember is that when you see the word or, that translates to an addition sign. The probability of event A and B occurring is actually equal to 0. So what that means is that we have no shared outcomes between A and B. There's no overlap. So the probability is equal to 0. Probability is always a number from 0 to 1. 0 means that the event cannot happen, and 1 means that it's certain to happen. Now let's look at our complement. The complement of an event is the set of all of the outcomes in the sample space that are not included in the event. So I'm going to come up with a new example here. Event A is rolling an odd number on a die. So the outcomes of an odd are 1, 3, and 5. The outcomes that are not odd are 2, 4, and 6. So the complement is the probability that we roll a 2, 4, and 6. Often we use the formula of finding the complement by taking the probability of 1 and subtracting the probability of the event. And where that formula comes from is that the probability of event A plus the probability of the complement is likely to happen, so it's equal to 1. So therefore, if we subtract the probability of event A from both sides, we get our formula. Standard number cube, they often use the word number cube instead of die. Ones. Let E represent the event that you roll an even number, and T represent the event that you roll a 3 or a 5. So what is our sample space? Our sample space are all possible outcomes. So that would be 1, 2, 3, 4, 5, and 6. E is rolling an even number. So that would be 2, 4, and 6. And T would be rolling a 3 and a 5. So let's make our Venn diagram. When I draw my circles, I'm going to do a quick check and make sure we don't have any overlapping outcomes. And we do not, so there is E and T. In T, I have 3 and 5, and in E, I have 2, 4, and 6. And then my sample space holds whatever's left over, so that would be a 1, and that's it. So what is the probability that you roll an even number or roll a 3 or a 5? So the probability of event E, because that's our even number, or a 3 and 5, is equal to the sum of each individual. So the probability of event E happening. Event E has 3 outcomes, so that's going to be in our numerator, out of a total number of possible outcomes. So when I roll a die, I have 6 different options that I could possibly get. For probability of T, I have 2 outcomes, that's the 3 and the 5, out of that possible 6. I add my fractions together. 3 plus 2 is 5 over 6. Next question has the same setup. Event E represents rolling an even, and T is a 3 or a 5. So what is the probability that you roll an even number and a 3 or a 5? So remember, and is asking the question if we have any or overlapping outcomes, and we don't. So that means the probability of E and T is equal to 0. We do not have any shared outcomes between E and T. What is the probability that you do not roll an even number? So this is our complement question. So think of it this way. The probability that we roll an even plus the probability that it's not an even has to be equal to 1. So if we want to find the probability that it's not an even, we will subtract the probability that it's an even from both sides. So the probability that it's not an even is equal to 1 minus the probability that it is an even. And we already found the probability of it being an even. The probability of it being even is 3 outcomes out of a possible 6. So we simplify this, we can make 1 6 over 6. So that simplifies to be 1/2. Now those questions worked out really nicely where we didn't have any overlapping events, but in the real world that's not actually going to happen all the time. So we're going to use the same idea of rolling a die, but we're going to look at the probability of non-mutually exclusive events. If we're finding the probability of event A or B, and yet we have some overlapping events, you'll see that the circles within the sample space overlap. So that means that we have some shared numbers. So we have the probability of A plus the probability of B, but then we subtract any of those overlapping numbers. So let's say these are our 2 events. Probability of A is an odd when we roll a die, and the probability of B is a number greater than 4. So let's actually write out what those possible outcomes are. For odd, we have 1, 3, and 5. And for greater than 4, we have 5 and 6. Now notice that 5 lives in both events. So if I was going to put this on my Venn diagram, I would have 1, 3, and 5, and then I would have 5 and 6. Now here's the problem, and so I'm going to fix this in a second. By having the 5 in A and in B, we've actually counted that outcome twice. So what we do is we take that probability of A, we add the probability of B, so we've counted that number 5 twice, but then we subtract the probability of A and B. So the reason that we subtract the probability of A and B is to avoid our double counting of an outcome. So I'm going to change what this looks like in our Venn diagram. I'm going to put the 1 and the 3 in the A, and I'm going to put the 6 in the B, and then I'm going to put the 5 in that overlapping space. So if I find the probability of this, the probability of event A is 3 over 6. The 1, the 3, and the 5, that's 3 favorable outcomes out of a total of 6. The probability of B is greater than 4, so that's 2 outcomes over 6. But again, we've counted that 5 twice, so we need to subtract. So we have 3 over 6 plus 2 over 6 minus how many outcomes are being overlapped? Well, that's only 1. So 3 plus 2 is 5, minus 1 is 4. So that would be our solution. So again, with non-mutually exclusive events, we have to subtract that middle overlapping outcome because we've counted it twice. A student-made target includes 2 overlapping squares. Assume that a sticky ball is thrown at the target and it's equally likely to land anywhere on the target. What is the probability that the ball lands inside one or both of the squares? So imagine these squares as our events and the big rectangle as our sample space. So our sample space would be 20 times 60 because we're talking about area. So that's 1,200. That's the total possible area. I'm going to say that the yellow is event A and the blue is event B. So the probability that A or B is equal to the probability of A plus the probability of B minus any of that overlapping, A and B. So what is the probability of A? Well, we're trying to figure out what the area is. So the area would be 10 times 10, so that would be 100 over the total possible area, which is 1,200. B would also be 10 times 10, so we have 100 over 1,200. And then our overlapping part is 5 times 5. So 25 over 1,200. So we add our numerators, so we get 175 over 1,200, and that simplifies to be 7 over 48. So the probability that the ball lands inside one or both of the squares is 7 over 48, which is approximately 15%. The next type of events we're going to talk about are called independent events. Independent events mean that we have 2 separate events, and one event has absolutely no impact on the next event occurring. So independent events, you'll notice that we use this word and when we're finding the probability, and that matches with a multiplication. Just like I said before, where the word or matches with an addition, the word and matches with a multiplication for independent events. So the example here is that we roll a die and we toss a coin. The results of rolling a die has absolutely no impact on what our result is when we flip a coin. So for example, the probability of rolling a 4 would be 1 out of 6. The probability of flipping a heads is 1 out of 2. the probability of doing both events together, so the 4 and the heads, we take that 1/6, we multiply it by a half, and we get 1/12. So example 3, a jar contains 12 green marbles and 8 violet marbles. So we have 12 green and 8 violet, and that's a total of 20. A marble is chosen at random, so that's a key element, and it is replaced. That's another key element. Another marble is chosen at random after the first marble. Does the color of the first marble affect the possible outcomes for the second marble? So here's the first marble. The probability of picking a green is 12 out of 20, which simplifies to be 3 out of 5. The probability of a violet is 8 out of 20, which is 2 out of 5. The question says that that marble is replaced, and then we pick a second one. So that means that all 20 marbles are back in that jar. So when we pick a second one, the probability of a green is 12 out of 20, which is 3 out of 5, and the probability of a violet is 8 out of 20, which is 2 out of 5. So the key here is that these are independent events, but the reason that they're independent is because of the replacement. So for independent events, the occurrence of one event does not affect the probability of the second event. Now we're talking about that same jar, 12 green and 8 violet. A marble is chosen at random, and it is not replaced. Another marble is chosen at random. Does the color of the first marble affect the possible outcomes for the second? So let's do this again. So we have our first. The probability of green is 12 over 20, which is 3 over 5. The probability of violet is 8 over 20, which is 2 over 5. It's not replaced. And let's just say, for argument's sake, that a green was picked. Now we go to the second marble. Well, if a green was picked the first time, then that means that we don't have 12 green left. We have 11. And it also means that our total has decreased by 1 as well. With the violet, because we didn't pick a violet the first time, we still have a total of 8, and our grand total of all marbles is still 19. Now this is an example where our events are dependent on each other because the probabilities have changed from one marble to the second marble. Example 4. Alex cannot decide which shirt to wear today, so she chooses one at random. The probability of rain is 40% or 2/5. So we're talking about a shirt and we're talking about rain. What is the probability that Alex chooses a yellow shirt and, see that word and, it does not rain? So if we look at our closet here, we have 2 yellow shirts out of 4. So the probability of yellow and it does not rain. Well, these are independent events because whether I pick a yellow shirt or not has absolutely no impact on if it's going to rain today. So that means that we are going to do a multiplication. So the probability of yellow times the probability of not rain. Now notice in the question that they gave us the probability that it will rain. So we actually need to find the complement. So the probability that it's not going to rain, remember our formula, is 1 minus the probability that it will rain. So 1 minus 2/5. If I find that common denominator, so 5 over 5 minus 2 over 5 is equal to 3 over 5. I go back to my formula. The probability of yellow is 2/4 times the probability of not rain, which is 3/5. When I have fractions, I multiply numerator, numerator, and denominator, denominator. So same setup of the question. Alex cannot decide which shirt to wear today, so she chooses one at random. The probability of rain today is 40%. What is the probability that Alex chooses a yellow shirt and it does not rain? So that's what we already found. So the probability of yellow and not rain, we just found that to be 3 over 10. Then it says, or that Alex chooses a green shirt and it rains. So the probability of green and rain. So let's find the probability of green and rain. So if we go back to our picture, we see that there's one green. So the probability of green and the probability of rain. So that's a multiplication because it's an and. So 1 out of 4 are the green shirts and rain is 2 out of 5. So we get 2 out of 20, which is 1 out of 10. Alex chooses a yellow shirt and it does not rain, or Alex chooses a green shirt and it rains. So we have that or. So that means that we're going to take our two answers and we're going to add them together. So our total is going to be 40%. Now I've put everything together in a slide for you. So mutually exclusive, no outcomes in common. It has the or with the addition. Independent, it means that the occurrence of one does not impact the probability of the other. It has the and the multiplication. And I know that was a longer video. There was a lot of new terminology and concepts. Thanks for hanging in there with me.